Hi everyone. So this is what the next couple of days will look like. We have our last lesson with applications today. You'll get the test review after the lesson, and you'll have it to start over the weekend. Hopefully, get some good headway on. Classwork on Monday. So a couple problems from today's lesson, a couple problems from yesterday's lesson. And then Tuesday and Wednesday will be full periods for you to work on the test review, and then we will test on Thursday and Friday. Friday will be the day that you take your test on the applications portion. Okay, hopefully then it'll be enough days that'll give you some time to work through those types of problems. And then Thursday will be everything else that is non-applications. Okay, so I'm going to start by actually backing up and then looking at one of your homework questions. If you notice on your answer key, I blanked out number 8, just because I wanted to make sure that you actually attempted it before just copying it down. So I thought we could go through it. I asked you a question where it says Russ and Shirley started a collection of coins when they first got married in 1942. They have been collecting only quarters. They started with 25 and had 1,800 in 1977. At this rate, in what year will they have 750? Okay, well, the problem with this question is the only way that you can answer it is by knowing at what rate they grew from 25 to 1,800 from 1942 to 1977. Okay. You could think about it this way too. If the question is asking at this rate in what year will they have $750, well, you could start the equation by saying 750, but we're talking about quarters here, not dollars, so I have to convert that into quarters. So I do 750 times 4. Let's see. So that means 3,000. So I would say I want to know when I'm going to have 3,000, which equals, and then we can use the 25 that we started with initially. And then this is where you get to here and you're like, well, I don't know what my rate is. And I want to also know in what year. So I have to make that X as well, but I don't know my rate, so it's too many unknowns. So what you can do is you can solve for your rate first, which is actually what you did in Math 2 last year. So I set up my equation here, and I said 1,800 quarters equals 25 initially, times 1 plus, because we know that there's an increase from 25 to 1,800, and that's a time period of 35 years. And then you divide by 25 raised to the 1 over 35, so raised to the reciprocal. And then you get that right here. You get that R then is about 13% increase each year. So then I can go back to this equation, and I can set my equation up. Let's see. So you can see here's my 3,000 equals 25 times 1 plus 0.13 raised to the x, which is what I didn't know there. Okay, and then I can use logs to solve, and I can see that it'll take about 39.17 years, or sometime in 1981. Okay? Okay, so let's look at today's stuff. On your notes, I have a warm-up for you, which I apologize, I didn't give you guys much space. I know there's less space than this. I actually found this question on an SAT. So you may want to write off to the side SAT. So I thought it fit in well with what we're doing, and it actually was a problem that we talked about yesterday. But this is how the SAT worded it. So it says the number of decibels, D, are produced by an audio source can be modeled by the equation. This is the equation we used yesterday, where I is the sound intensity of the audio source and K is a constant. How many decibels are produced by an audio source whose sound intensity is 1,000 times the value of K? So, notice they use K instead of I sub O, but same idea. So it says how many decibels, well that's our D, so that's what we don't know. So how many decibels equals, and we'll say 10 log, and then we have to figure out what to put in here. And that's where the hard part kind of comes, because it says 1,000 times the value of K. But it's pretty much the same as what we did yesterday. Different wording, but same thing. So if it's 1,000, if the intensity is 1,000 times the value of K, then I can just say K is something, which whatever this is, then this would be 1,000 times A. You can see it's pretty much the same thing as yesterday. And then what happens is the K's cancel, and then D is equal to 10 log of 1,000, which we could put into our calculator, or we could actually evaluate as well fairly easily. But I'll just use my calculator so we can get to the notes. So 10 log of 1,000, so 30. So it would be 30 decibels. But yeah, so that's how the SAT worded it. Okay, so let's get into some new formulas. To calculate the pH of a aqueous, I think, solution, you need to know the concentration of hydrogen ions and their moles per liter. pH has to do with like your pools, like your water. The pH is then calculated using this equation. Okay, it says find the pH of a 0.0025 mole, I think that's hydrogen concentration solution. The HCl is a strong acid and 100% ionized in water. The hydrogen ion concentration is 0.00525 moles. Okay, so some verbiage in there that kind of gets confusing. But notice it says find the pH. So that's a good way to start by just saying, okay, well in this equation then I don't know the pH, so I know that then I'm going to call that x. I'm going to say x equals negative log, and then that right there, this is talking about what this is. This is your moles, which it has to be because I already don't know x. So then I'm going to say 0.0025. And then you can notice that x is already isolated, so all I have to do is put that in my calculator. Okay, so I'll say negative log 0.0025. Okay, and then I can say that x is about 2.60, and that's pH. Where the pH is about 2.60. Okay. Alright, so that was just an evaluating. Next one, what is the hydrogen ion concentration in a solution that has a pH of 8.34? So now we know the pH. So we're going to say 8.34 equals negative log. And then instead of using all those variables, I'm just going to say of x, since I don't know what it is. Okay. I cannot take the log of both sides. I don't even have an exponent, so it wouldn't make sense. But I can rewrite. First thing that I need to do is I always have to get rid of that coefficient. So I'm going to divide by -1, divide by -1, and that's going to give me negative 8.34 equals log of x. Now I'm going to rewrite, so I'm going to do this. That gives me 10 to the negative 8.34 equals x. So x is already isolated here. You guys can say this is your answer. I'm good with that. If you want, you can put this into your calculator, and you can say 10 to the negative 8.34, and it gives you that. So, or you can say, so I'm going to put or, you can say that x is about 4.57 times 10 to the negative 9th. Okay, so either of those answers is fine. I feel like this is a little bit more complicated because you have to use scientific notation. Remember, scientific notation only has one number to start with. And then that E is your times 10. Okay? Let's try the next one. A chemist is trying to arrive at a pH of between 8 and 8.9 For a chemical mixture, write an expression representing the difference in hydrogen ion concentration over this pH range. So some of the important wording that comes up in this problem is the fact that this is talking about a range and that we're trying to be between these two. So what happens is we actually have to figure out, we have to basically solve two problems. We have to know when our pH is 8 and 8.9. So I'm going to say 8 equals negative log of x, and then I'm also going to say 8.9 equals negative log of x. So I'm solving two different equations. I want to know what it's going to be between. Divide by negative, so negative 8 equals log of x. Over here, negative 8.9 equals log of x. Okay, rewrite like we did in the last step. I get 10 to the negative 8 equals x, and 10 to the negative 8.9 equals x. You can convert those if you are, they're already in 10 to the negative 8 power. You can convert them if you want. I would just leave them. But here's how I have to interpret it. I want to know the range, so I'm going to say between, and we typically say our smaller number first. This is my smaller number. It's raised to a higher negative power. So I'm going to say between 10 to the negative 8.9 and 10 to the negative 8. Okay, so that is my range. Alright, let's move on to a new equation. This equation is going to come up in a couple of different types of problems, but it's Newton's law of cooling. It's got a lot of t's you can notice. You've got t equals t sub 0 minus t sub r times e to the negative rt plus t sub r. Notice these two variables are the same. Okay. Alright, so then it kind of explains what the variables mean. So the initial temperature is T sub O. T is the temperature after T minutes. This is very important that this is talking about minutes, not hours. Okay. T sub R is your surrounding temperature. You can think about that as like your room temperature. And R is the cooling rate of the substance. Alright. You are cooking something. It's an Ethiopian stew. When you take it off of the stove, its temperature is 212. The room temperature is 70, so I'm going to write here that that's T sub R. So that's the 70 degrees right here. And the cooling rate for the stew is, so that tells us nicely that that's our R. How long will it take for the stew to cool to a serving temperature of 100 degrees? Okay, notice it says how long. So how long is just our lowercase t up there. So I'm going to put the lowercase t right there. Okay, so that kind of helps me fill in a lot of questions. Okay, when it says right here, how long will it take for it to reach a serving temperature of 100 degrees, that is your capital T. That's the T right here, where it says T is the temperature after T minutes. Okay, so that means time has gone by and I want it to reach 100. So if you notice, the one that we haven't filled in yet is T sub O, which means that that must be this. So process elimination is good when you have this many variables that you have to substitute in for. Okay, and that's the T sub O because that was the temperature and we want it to cool down to 100. So that's the initial, this right here is the end. Okay, so now we're going to fill in. So T is 100, so I'm going to say 100 equals, and then T sub O, which is 212, minus the room temperature, which is 70, times E. And be very careful here. It's very easy to notice this negative R and just think that it's this R. But it's actually negative 0.046. And then times my time, so I'm just going to say X. And then plus that same room temperature, which was 70. Okay, so we should start by noticing that we are going to have to do a log somewhere in here because we have a variable that's an x. I want to move my constant over first, so I'm going to subtract it, which gives me 30. equals, and then I'm going to combine those two. So 212 minus 70, 142. Alright, so I get 142, and then e to the negative 0.046x. Okay, I need to get rid of my coefficient, so I'm going to divide by 142. Okay, now I could check and see if this is going to give me a nicer number. I just assume leave it. So I'm actually just going to leave it as 30 divided by 142. That way if it's not, I don't need to worry about it. Equals e to the negative 0.046x. Okay, I like to use a different color here if you noticed from yesterday. Just to kind of show. I can take the log or natural log of either of these to get this down, but I'm going to specifically take the natural log of both sides because of the e. Okay, so as soon as I write the natural log in, I know that this comes down and that's gone, so it just drops straight down. Over here. So then on the left side, I have the natural log of 30 divided by 142 equals negative 0.046 times x. So my last step is to divide. So you can see at this point I haven't really used my calculator for anything substantial besides just subtraction. But now I do. Alright, so we have this. Gives us that. Notice it gives us a negative, which is why it's very key that we are dividing then by a negative. Otherwise we'd get a negative time. Okay, we get that. Alright, so we get that x equals, remember that our t value up here was talking about minutes, so this means that this will take about 33.79 rounds up to 80 minutes. Remember, time can be a decimal, so make sure that you actually write as that, don't round it up to 34. So this is going to take about 33.80 minutes. Okay, so that's one type of application that we can do with Newton's cooling law. Flip over, we're going to do another one. Oops. Let's see. Come on. I did not write the equation in here, so why don't you guys take a second and pause it if you need to and write this equation so you don't have to flip back to the front to see it. Anytime that you are given this type of problem, I will give you the equation and I will define what these things mean again. I will not expect you guys to memorize this. Okay? Okay, so now that you have this formula written down, so here's another type of problem that you can answer with it. It says a coroner is called to investigate the time of death of a person that died somewhere between, sometime during the night. At 11 a.m., the coroner measures the temperature of the body to be 75 degrees Fahrenheit. The room temperature was a constant 64 degrees. So I'm going to say right here that that's T sub R, just because it's kind of an obvious when they say room temperature. And the cooling rate for a human body is, so that's nice, we have the R value. There are going to be questions where I ask you for the R value. Assuming a normal body temperature of 98.6 at the time of death, approximately when did the person die? Notice that when is talking about a time, so that means that t, that lowercase t is what we're going to be solving for, which means we must know everything else. Okay, well, looking back, I know my R value, I know my T sub R value, I need to find my T and my T sub O. Okay, so my T value is the temperature that is current. Okay, so if you think about the last problem, I'll flip back over to it real quick. The T value in this one was the 100 because that was what I wanted it to get to. I wanted to know when it was going to get to that temperature. Whereas in this one, my T value is saying that the temperature is 75. That's my T value because that's what it's at now. And I want to know how did it get there. Okay, or if you didn't really, like, it's kind of confusing with that. But this right here, when it says we can assume a normal body temperature, that has to be my T sub O, because when the person died, that was the original temperature, and then their body temperature dropped to 75. So their original was that, and then which leaves this over here having to be the T value then. So again, process elimination can be helpful. Sometimes it's hard to differentiate between the T sub O and the T. Okay, so let's do some filling in. So my T then is 75. My original is assuming a normal body temperature, so 98.6. Minus the room temperature, which is 64, times E. Don't forget your negative here, so negative 0.0016666, and then times my time that I don't know, and then plus the room temperature, which was 64, chilly room temperature. Okay, same steps that I did before. I'm going to subtract my 64 to the other side, which gives me 11. Okay, and then I'm going to subtract those two numbers inside. Let's see, so 98.6 minus 64, so 34.6. Times E to the negative 0. Be careful you don't lose a 0 here or any numbers. Okay, same as last time. Next step is to divide by the coefficient. Okay, I'm not going to waste my time substituting that in. I'm fairly certain because of that decimal it's not going to work out. So I'm just going to leave it as this. So it's exact equals E to the negative. Don't lose your negative. Okay. Alright, I need to pull this exponent down, so because that's E, I'm going to use natural log. Comes down. This cancels, so it just drops. Okay, so I get the natural log of 11 over 34.6 equals negative 0.001666x. So you can see, to get this by itself, I'm going to divide. So the nice part is once you start using logs, you should see a pretty consistent pattern in how you solve. Alright, so let's put this into our calculator. Alright, be careful of the decimals. Negative 0.001666. Just double check your numbers. You'd hate to do everything right and then lose a number in your calculator. Okay, and we get that. I'm just going to pull this up over here. So I get that x is about, remember x is talking about minutes, it's the way the formula is defined. So I'm going to say about 687.85 minutes, which is a lot of minutes. So a reasonable question would be to ask you in hours, but this question asked, let's see, it said approximately when did the person die? So when is not talking about in 687 minutes, when is talking about a time. Notice that in the beginning of the problem it said that the coroner recognized this happening at, or he measured the temperatures at 11 a.m. So I need to figure out what this means in terms of 11 a.m. So the first thing I'm going to do is convert this into hours. Okay, so I'm going to take, oops, I lost that time. Let's see. Okay, so this is what I have in my calculator. I'm going to take this and I'm going to divide by 60 because there's 60 minutes in an hour. So then that tells me that there is about 11 hours. And then I need to convert this into minutes. So I know that there's about 11 hours, but then I'm going to take 0.46 and I'm going to multiply it by 60 minutes so that I can convert that into minutes. Okay, it's not 11 hours and 46 minutes. There's not 100 minutes in an hour. So I need to take 0.46 of 60. So I'm going to take 0.46 times 60. And it tells me it's about 27 minutes. So 11 hours and about 27.6 minutes. Okay, and at that point you can just convert that to 28 because round up. Okay, so I want to take 11 a.m. and I want to fast forward 11 hours and 28 minutes. Okay. Okay, so if we're at 11 a.m. and we add 11 hours to that, that puts us at 10 p.m. And then the 28 minutes would be our 28. So this would be 10:28 p.m. Actually, so our time is right. It's 11 hours and 28 minutes, but this answer's not right. This person died during the night. We have to go backwards. Sorry, not forwards. The coroner recognized this at 11 a.m., but the body obviously died before that, so we have to go backwards. So if we go backwards 11 hours from 11 a.m., that puts us at midnight, and then we have to go backwards 28 minutes from there, which puts us at 11:32 p.m. Okay, so just to kind of recap, because I feel like I was all over the place. So we found our time. That should be pretty systematic. We found that it was about 687.85 minutes. We converted that into hours by dividing by 60. So I just put a divided by 60 under here. Okay, that gave us our 11 hours. We had to take our 0.46 out of 60 to give us that it was about 28 minutes. So we then had to say, okay, if the person was measured, was recognized or found or whatever at 11 a.m., then 11 hours and 28 minutes in the past is when the person had died. So you have to go backwards 11 hours, which puts you at midnight, and then backwards 28 minutes from there, which puts you at about 11:32 p.m. Okay, so maybe this problem is decided that you want to go into being a coroner. A lot of math involved. Or maybe not. Maybe you don't want to do logs in your career. All right, the last problem is fairly simple. Kind of threw it on there just as a review for you. So you can pause this and try it, and then check your answer. Okay, so assuming you are checking your answer here, I'll do it kind of quickly. It just says the population of P of a bacteria in a culture after T minutes is given by the equation given, where P sub O is the initial population. If the number of bacteria starts at 450, so we'll say 450 times 1.23, which means an increase of 23% because it's 123. How long will it take for the population to increase to 5,000? So I'm going to make this x because that's my time equals 5,000. Okay, so first step is to divide. When we divide, it divides nicely, but I don't want to pick up a calculator yet. So I'm just going to cancel out the zeros and say that this is 500 over 45. It would simplify very nicely though because divide by 5 equals 1.23 to the x. Okay, I'm going to take the log of both sides. You could take the log or natural log, it does not matter. Brings your x down. So the log of 500 divided by 45 equals x log of 1.23. Okay, last step, divide by log of 1.23. Alright. And remember, whether you put, no matter what answer you put in your calculator, if I do the log of 5,000 divided by 450, it will give me the exact same thing as the log of 500 divided by 45, and same thing if I simplified that further. Right, but I'm taking that answer and I'm dividing by the log of 1.23, and I get that x is about 11.63, and I can't remember what this problem was asking. This was in minutes, and it says how long will it take for the population to increase. So it'll take about 11.63 minutes. It's quick. Okay, and then that's it. You can go to your test review. So just again to give you an idea, these are the equations that you are going to have to know for the test. Okay, so here is your compounding continuously. Here is your compounding problem. So just a normal compounding. And then here is your problem where if it's doubling for a certain amount of time, typically we have to use this one. The only one that I keep forgetting to put on here is the y equals a times 1 plus or minus your rate raised to the x. So that's like the problem that we just did if you're increasing or decreasing by 1%. Okay? So you will have to have those memorized. Alright? And then your test review. Alright, notice that I think it's the first 1, 2, 3 pages, 4 pages. Yes. So the first 2 full pages, front and back, are all about the stuff that will be on Thursday. And then the last problems are all about what you will have on Friday. Okay, there is a lot of problems, but there's, a lot of different wordings and manipulation that can be done. So good exposure. All right, try to get a good head start over the weekend. That way, a little less work during the week, and then that way you can leave spring break hopefully on a high note. Okay? All right, have a good rest of your day, everybody. I'll be back on Monday if you have any questions.